Hi, in this video and in perhaps a few more that follow, I want us to look at the properties of exponents. So let's start by defining exponents. So let's suppose we have this product here, 5 times 5 times 5 and so on. Well, we all know that one way to express this is to say 5 to the 7th power. And so this gives us our starting definition of an exponent. It's simply the number of times a number appears in a multiplication. So here we have 7 to the 3rd power, and the 7 appears 3 times. 2 to the 5th, the 2 appears 5 times. Exponents don't have to be integers, but for now we'll limit our definition to integers. Shortly we'll expand on this definition. You should be aware that exponents are also called powers and indices. So here we can also say the power here is 3, or the index here is 3. Here again we have the definition of an exponent. The exponent here is n, and saying a to the nth power simply says that in the multiplication here a will appear n times. Once again we have it here. So a to the n is a times a and so on, and you will have n of these a's. This symbol means that this is the equivalent of this. This goes a bit further than your standard equal sign. When you say, for example, x plus 1 equals 3, that is only a true statement if x is 2. But this is true always. So this is an identity, and so whenever the equality is actually an identity, then we use 3 bars here instead of 2. Here now we look at our first law per se of exponents. If I have a to the mth power and I multiply it by a to the nth power, that's the same as saying a to the m plus n. So let's skip ahead here and see the example that I'm talking about. If I have 5 to the 4th power and I multiply it by 5 to the 3rd power, well, the exponents add up. So this becomes identical to 5 to the 4 plus 3 power, which is 5 to the 7th power. So let's see how this makes sense. It's always important that you see some kind of intuition in these things. It should make sense to you. It shouldn't just be like some crazy formula you are memorizing. So here, let's suppose we have 5 times 5 times 5 times 5, and then we're multiplying that by 5 times 5 times 5. Of course, we know that this is the same as 5 times 5 times 5 times 5 times 5 times 5 times 5. In other words, this times this gives us this. That's 5 to the 4th, and that's 5 to the 3rd, and we know that's going to be 5 to the 7th. We simply observe that this 7 can be obtained by simply adding the 4 and the 3. In other words, the number of times that 5 appears in this multiplication is the number of times it appears in this one, and the number of times it appears in this one. Of course, this needs to be a multiplication here. So that's pretty much it. A to the m times a to the n is a to the m plus n. So we can look at other examples of this. And so let's say we have 6 to the 5th times 6 to the 8th. Well, that's going to be 6 to the 13th. This should be very obvious. This multiplication has 5 6's in it. This multiplication has 8 6's in it. In all, you have 13 6's in the multiplication. Okay, so now we have two properties. A to the m times a to the n is identical to a to the m plus n. So now let's look at this law or property of exponents. We have that a to some power m divided by the same number a to some power n is identical to a to the m minus n. Let's get some intuition now for this. Here we have 5 times 5 times 5 times 5, and 7 5's up here, and 5 times 5 times 5 times 5. Now, you should realize that this is the same as 5 times 5 times 5. So let's see how we get that. We can say, well, this 5 divided by this 5 gives me 1. This 5 divided by this 5 gives me 1. This 5 divided by this 5 gives me 1, and this 5 divided by this 5 gives me 1. So obviously, I get a lot of divisions occurring here, resulting in 1. So if I have 7 up here and 4 down here, well, then we'll have 4 in common, leaving me 3 up here. So that's what we're saying here, that this obviously is 5 to the 7th, and this is 5 to the 4th, and we know by doing it manually that this will be 5 to the 3rd. 7 minus 4 will indeed give us 3. So we can see that this intuitively seems correct. So this should not be something hard for you to remember. Let's take a look at an example here. If I have 8 to, let's say, the 11th power, and I divide it by 8 to the 6th power, well, I'll have 11 of these 8's up here, and I'll have 6 of these 8's down here, and then I get all those divisions occurring, and I'll be left with how many 8's on top? Well, if I have 11 up here and 6 down here, I'll be left with 8 up there. So, sorry, with 5 up there. This gives us 11 minus 6, 5. So now we have 3 properties here. So our little list is growing. A to the m divided by a to the n is identical to a to the m minus n. So make sure you see the sense of this. This will be almost impossible for you to remember if you just memorize these by rote without getting the meaning of these things. Here is a property that can seem rather arbitrary, and it's that anything raised to the 0 power is going to be 1. So let's see how we can show that this is not so strange after all. If we have 5 times 5 times 5 times 5 divided by the same thing, we know this is going to be equal to 1. Why? Because we know that whenever we divide something by itself, we get 1. That's what we're saying here. But we know, given our previous rule, that this is 5 to the 4th, and this is also 5 to the 4th. And we know, given another previous rule, that this can be expressed as 5 to the 4 minus 4. And we know that 4 minus 4 is 0. So, since we know this is equal to 1, well, 5 to the 0 must be equal to 1. We could do this with the number 6, number 10, with any number, and we would very soon realize that anything raised to the 0 power 10 has to be 1. So no, this is not like an arbitrary law. Somebody didn't just say, hey, let's make this equal to 1. It makes sense based on our previous laws. So our little list is growing now. A to the 0 is equal to 1. Here's another property that seems strange at first, but then makes sense once you think about it carefully. This property states that a to the minus 1, any number to the negative 1 power, is going to be the same as 1 over a. Remember that a can't be 0 here because we can't have division by 0. So how can we see that this has to be true? Well, let's take a look at this little example here. 5 times 5 times 5 divided by 5 times 5 times 5 times 5. Well, we can do the same little thing that we did just now. 5 divided by 5 gives us 1. 5 divided by 5 gives us 1. 5 divided by 5 gives us 1. That leaves us with just 1 5 under here, so that's 1 over 5. So in other words, this expression here is equal to 1 over 5. However, we can write this as 5 to the 3rd power and this as 5 to the 4th power. And remembering the rule we have already established, this then can be expressed as 5 to the 3 minus 4, which gives us minus 1. And so now we are forced to accept, since we have already accepted the previous properties, that 5 to the minus 1 is indeed 1 over 5. Make sure you understand this, and this equation then should be, this identity should be easy to remember. It should make sense. It's not arbitrary. Anything to the minus 1 power is the reciprocal of that number. 8 to the minus 1 is 1 over 8. 2/3 to the minus 1 is 3/2. 5/8 to the minus 1 is 8 over 5, and so on. Now we come to this property. As you can probably see, this is very similar to the one we learned just now. Only instead of minus 1, it's minus n. So this property simply extends the previous one to values other than 1. So n to the minus n is identical to 1 over a to the n. The intuition, 5 times 5 times 5 divided by 5 times 5 times 5. Well, we have 7 of them here. Let's do a little division. 5 divided by 5 gives me 1. 5 divided by 5 gives me 1. 5 divided by 5 gives me 1, leaving me 4 of them under here. So we now know that this is equal to this. Of course, this is 5 to the 3rd power, this is 5 to the 7th power, and this here is 5 to the 4th power. If you use the property we learned a short while ago, this can be expressed as 5 to the 3 minus 7, which is 5 to the minus 4th power. So this is saying that 5 to the minus 4 is equal to 1 over 5 to the 4, which is what this was saying at the beginning. We can extend this to other examples. We can say, for example, 2 to the minus 3 is equal to 1 over 2 cubed. I can even notice 1/2 is the reciprocal of 2, so we can say here, for example, x over y raised to the minus 8 is 1 over x over y, or better yet, y over x, the reciprocal, to the 8th power, and so on. So our little list is growing. We come now to this property. If we have a product which is raised to some power, then that power applies to each factor in that product. So let's see if we can see the intuition for this. Let's suppose I have 5 times 3 quantity squared. Well, that's the same as 5 times 3 times 5 times 3. So let's see where this takes us. We can remove these parentheses by simply saying 5 times 3 times 5 times 3. And then we can rearrange them. It's still the same thing, 5 times 5 times 3 times 3, and we see that this is 5 squared times 3 squared. So this one should not be hard for you to remember. And we add this one now to our list of properties. So just now we looked at a product raised to a power. Now we want to look at a quotient raised to a power. And similarly, we see that the power affects the numerator and the denominator. So let's get the intuition for this. Here's an example: 5 over 3 squared. Well, that's the same as 5 over 3 times 5 over 3. If we follow this, we realize that we don't need these parentheses to begin with. 5 over 3 times 5 over 3, and we can write this as 5 times 5 over 3 times 3. That's 5 squared over 3 squared. So should be clear then that this is true. This is not proof. Remember, we're just getting a sense of it. But this should be good enough for you to help you remember this. And once more, our little list grows. We now come to this property where we say that a number raised to a power and then everything is raised to another power. Well, it's the same as raising that number a to the product of these powers. Now for the intuition: 5 to the third power, everything raised to the second power. Well, this is something squared. So that's 5 to the third times 5 to the third. Let's follow it. This is 5 to the third times 5 to the third. But we already know that when we have equal bases in a product, the exponents add up. So that's 3 times. That's 3 plus 3. Of course, 3 plus 3 is the same as 2 times 3. So we see then that 5 to the third power, everything raised to the second power, is 5 to the 3 times 2, or 2 times 3. Remember, multiplication is commutative. So a to the mth power, everything raised to the nth power, is a to the m times n. And that's what we see here. When I put together this list, I forgot the most obvious one. Anything to the first power is just that number. So 5 to the first power is 5, 8 to the first power is 8. So we don't normally write this 1 here unless we want to bring your attention to the fact that there's a 1 there, as I did in one of the previous examples. Anyway, that's it for this video. We go over a little bit over the 10-minute mark, but I don't think we go over too much. I'll see right now when I edit this. Okay, bye and thanks for your attention.